Chair, presenters, and all the participants or guests of these sessions. Welcome to the Technical Paper Session 2C of the BLSI Design Conference 2021. The session chair for this session is Swati ji. She is from Texas Instrument. So there are 5 papers to be presented in the sessions. Every paper will get 20 minutes, 15 minutes for presentations and 5 minutes for question answers. All the attendee or guests can ask questions by typing questions during the presentations on the question and comment box on their viewing screen. Once presenters finishes his or her presentations, we'll have question answer sessions. Now let me hand over the session to the session chair. Swati, please take.
Okay. Thank you, Professor Sahu. Hello, everyone. A warm welcome to everyone for the session Test Reliability and Verification. So as Dr. Sahu has mentioned, we have interesting presentations lined up for today. And without further delay, let's go into the presentations. Just one reminder again, please type your questions in the Q&A box at the bottom of your screen, and we can take those questions at the end of each presentation. Okay, so the first paper for today's session is Automated Low-Cost SBST Optimization Techniques for Processor Testing, and the presenter is Dr. Vasudevan from IIT Guwahati. Over to you, Dr. Vasudevan. Hello.
Optimization techniques for processor testing. Hi everyone, myself Vasudevan. In this paper we discuss automated low-cost SBST optimization techniques for processor testing. Software-based testing is one of the most modern testing techniques for processors. So in this technique, we execute normal sequences of assembly code instructions on the processor and get the response and compare this response with a golden response, that is expected response. If these responses matches, we say that there is no fault of code. Otherwise, we say we declare a fault. So the inputs will be self-test code and the self-test data upon which this code is executed, and the output will be the self-test response, which will be compared with the expected response. And the advantages are at speed testing. At speed testing is testing the processor at the operational frequency of the processor and non-intrusiveness. That is, we are not modifying any design, or we are not adding any extra like additional hardware circuitry for the sake of testing. So, SBST delivers at speed testing for modern complex processors. So at speed testing is very important factor for SBST. So to deliver this at speed testing, we need smaller test programs with lesser execution time. So test program compaction is a very important factor in SBST life cycle. So, also we need to maintain the fault coverage that is given by the test program, along with reducing the test program size or execution time. So in 2016, Godesi et al. Have proposed 2 algorithms. One is A0 algorithm and one is A1XS algorithm. In A0 algorithm, redundant instructions will be removed from the test program. That is, we take the test program and we take the instructions one by one from the test program and see whether these instructions are contributing in fault coverage. If not, we remove these instructions one by one. So it is a very costly method. And instruction block restoration method, which is A1XS algorithm. In this, we remove blocks of instructions and restore instructions one by one and see whether they contribute to fault coverage. So as this is a block-wise method, this has lesser computational effort, but this gives lesser compaction rate. So altogether, these methods have good compaction but consume high computational effort. So, we desire like the desired technique will be having high compaction rate, but will have lesser computational effort. So we propose a 2-stage technique in which the first stage is independent instruction removal. Initially, we convert the test program into a data dependence graph. So in this test program, all the instructions are dependent to each other. So we do not have any multiple subgraphs in this technique. But in this example, the test program is converted into multiple subgraphs, multiple data dependent subgraphs. Suppose if G2 has a certain fault coverage, which like G2 covers a number of faults which are covered by G1, which are covered by the instructions in G1. In that case, we can remove G2. That is, if any of the subgraph has detects the faults that are already covered by any other subgraph, we can remove the redundant subgraph. So, but this is an elementary technique. We cannot guarantee that all the redundant instructions are removed in this method. But also the computational effort is very less because we need to have only single fault simulation in order to remove the redundant instruction subgroups. So we have proposed a more complex but more complicated and technique, which is based upon the block restoration method. So in block restoration, we convert the test program into a certain number of blocks. There are two types of block restoration techniques. One is bottom to top and one is top to bottom. In bottom to top technique, the bottom to top technique will be used by the conventional test compaction methods that we already discussed in the previous method. Godese et al. Have proposed two algorithms. One is instruction block restoration technique. So this instruction block restoration technique will be using the bottom to top restoration of SBST program. So in this block restoration, corresponding to each block, there is a set of reliant faults. So suppose block 5 has a set of reliant faults. A set of the reliant faults is the fault detected by the instruction for the first time. Suppose an instruction in block 5 detects a particular fault for the first time, which is not detected by the instructions in block 1 to block 4. That is called reliant fault corresponding to that instruction in block 5. So the conventional method uses bottom to top restoration method. Initially, we remove block 5 and add instructions one by one until all the reliant faults in block 5 is detected. And we go for block 4 and so on. But in top to bottom method, we will be restoring blocks from top to bottom. So the benefit of bottom to top method is when we reach the topper blocks, already the lower blocks will be compacted. So the fault simulation time will be very less. But in the advantage of top to bottom method is when you go for when you do bottom to top method, some of the critical instructions in the lower blocks will be missed. Some of the critical instructions suppose in block 5 there is an instruction which which can detect many of the reliant faults in the upper blocks. It may be removed during the bottom to top restoration. So, but in top to bottom restoration, it will not be removed. When we remove the instructions in block 1, we restore the instructions in block 1 by one. We will be seeing whether all the reliant faults in block 1 is detected by the below blocks. So we will not remove any critical instructions in top to bottom method. So in that way, compaction can be better. So instruction blocks. When you discuss about top to bottom method, the cost will be higher and the compaction will be lesser because bottom to top is less costly. The lower blocks will be already compacted. So to reduce the cost of top to bottom restoration method, we introduce the concept of logic simulation. In logic simulation, high-level logic simulation, we simulate the instruction encoding and syntax with the help of high-level programming languages. So all the instruction operation will be simulated using high-level operations, high-level language operations. So instruction blocks are evaluated using logic simulation, so that the cost will be lesser for the top to bottom method, and the contents of observable locations will be evaluated using this. So with the help of the contents of the observable location will be the state of the restoring block, and this state will be the state of the top block will be replaced with fewer added instructions. So this example will explain this. When you restore the block 4 and when you while restoring block 4, the top blocks is already restored, and we can do the logic simulation of the top blocks so that we can get what are the observable locations of the top 3 blocks, and what is the state, what are the states of the processor using the logic simulation, and correspondingly a fewer number of instructions can replace the top 3 blocks. So initial state of 4th block will be applied using fewer store and load instructions, and they will replace the top 3 blocks. So the reduced test program will have fewer instructions, and the fault simulation will be faster. So these are the results of test compaction. In method A0, we get a like CRS. CRS means the compaction ratio of size. If compaction ratio of size is more, that means the compaction is more. Compaction is lesser, and vice versa also. And CRS, of course, A0 method, which is a very intensive method, which takes each instruction and checks its redundancy. So CRS and CRT will be very less, but the cost will be very huge, 197. But for A1XX method, which is block-wise restoration, the CRS and CRT will be average, not that great, but the cost is lesser. But with the help of proposed stage 1 and 2, finally after stage 1 and 2, we get a CRS and better CRS and CRT compared to the A1XX method with a very less cost of 142.33. The CRS will be nearly 0.81. So the conclusion is we have our method gives an effective and effortless test program compaction with an enhanced compaction ratio of 0.812 with a lower cost of 142.33. So better this can be improved with the help of instruction reordering technique, so that further redundant instructions can be removed. So these are the references. Mainly our the 5th paper is our baseline paper, and GoDC, which is a paper on IEEE transcription of computers. Thank you.
Hello all, welcome to the 34th.
Okay. Yeah, thank you, Dr. Vasudevan, for the nice presentation. Now the floor is open for question and answers.
So from the audience, we don't got any questions. So now maybe session chair may ask 1 or 2 questions, or maybe from our other presenter may ask questions if they want.
Okay. So yeah, one question from my side. So when we are saying we have performed the logic simulations to identify the redundant instructions, right? How is exactly the logic simulations performed, and what tools have been used to determine that?
Yeah, so we actually replicate the instruction execution with the help of high-level language. Like I have used C programming languages, and all the instruction syntax and encoding will be replaced, simulated using a C program. So it is, of course, it is less accurate because it is a high-level simulation method. But ultimately, we get finally we get the all the observable states, actually observable all the contents of the observable locations. So that is what we need for in this approach, like for restoring the topper blocks or for replacing the topper block. So we do the logic simulation for the topper blocks, and we replace the state of these top three blocks using the contents of the observable location that we got from the logic simulation.
Okay.
Yeah. So that's a high level method. Of course, accuracy is lesser, but we get the observable states actually.
Okay.
Yeah.
So detail of jargon is not given in the PNDSM. Otherwise, you have a lot of actually state space simulations for that.
Okay, understood.
Yeah.
Thank you.
Thank you.
Any questions from anyone else? Okay. I think we have 4 more minutes for this session. Do we want to continue with the next paper or wait for more?
Okay.
All, welcome to the 34th International Conference. Hello all, welcome to the 34th International Conference on VLSI Design and the 20th International Conference on Embedded System. I am Anjali and I did my Masters from IIIT Delhi. Thank you for coming today. I am going to talk about reduced March IC- test for detecting aging-induced faults in memory address decoder. The paper is written by Kumari Anjali, Shubham Shah and Dr. Anush Grover, and I am going to present the paper. Proceeding towards the next slide. So first of all, I'll discuss about the agenda, that is list out the things which I'm going to cover in the PPT. So it involves introduction, types of faults in the address decoder, March IC-, proposed reduced March IC-, simulation setup, fault injection and results, conclusion. Proceeding towards the next slide. So first slide is introduction. Life critical applications like automotive applications uses huge amount of on-chip SRAMs for various applications like high beam control, radar fusion center, blind spot detection, side impact assist, and so many things. So for the entire these applications, definitely chip will be required, and any chip contains both logical as well as memory operations. So with time, aging of chips will occur and failure of chip will occur, so which will ultimately cause to the accident, that is life critical applications. So what can be the solution? Safety features can be added in SRAMs, or memory could be tested at every power on or at every fixed interval. If memory will be tested at every power on, so definitely memory will be unavailable for few minutes or for few duration of time. So short test time will be desired so that we can test our memory. Memory testing also includes testing of the periphery of the memory to detect peripheral faults. One such periphery fault is address decoder fault. A memory consists of two things, a memory array and memory periphery. So memory periphery includes like address decoder, row decoder, column decoder, pre-charge circuitry, sense amplifier, write driver, muxes, and so many things. So here we pick one of the periphery element, that is address decoder, and we injected fault into that particular address decoder, and we try to detect the faults of the address decoder using various algorithms, which we will discuss in the coming slides. So proceeding towards the next slide. So here I'll explain what are the types of faults in address decoder. Types of fault in address decoder. So it's AFNA, AFMC, AFMA, AFOC. AFNA is an address is not able to access itself. AFMC is an address uniquely access multiple cells. That is, this is the only address accessing those cells. AFMA is a cell is uniquely accessed by multiple address. That is, all these address only access a particular cell. AFOC is an address additionally access other cells. Mainly, the address decoder faults are the open circuits and the resistive open. Now, classification of resistive open. So it consists of intergate opens and intragate opens. Intergate opens are present between the logic gates. Intragate opens present inside the logic gate. So in the next slide, continuing the types of faults in address decoder. So this is intergate faults and this is intragate faults. So here we can see that if we consider this particular diagram, so here we can see, suppose that this is any gate, like this is AND gate, NAND gate, or any gate. So here we can see that RDF3 is inserted inside the gate, that is between the like inside the gate. It is inserted inside the gate, and this is here. This is not inserted any in the inside the gate. It's here and here only. So here we call this as intergate faults, and here we call this as intragate faults. So through these two examples, we can clearly understand what is the difference between intergate faults and intragate fault. So by injecting these two resistors here, faults will be produced, and one will be called as intergate faults and another one will be called as intragate faults. Now proceeding towards the next slide. So to detect all those faults, March IC minus. So March IC minus is used. So our algorithm, that is our proposed reduced March IC minus algorithm, is based upon the March IC minus algorithm. So it is essential to understand what is March IC minus algorithm, what is the complexity of March IC algorithm, and how we are going to use the March IC minus algorithm, and what is the Sachdev algorithm. So to detect any ADF, like for detecting any ADF, fault should be sensitized during the write operation and observed during a separate read operation, such that two address should have Hamming distance is equal to 1. So through example, I'll explain what is the meaning of Hamming distance is equal to 1 in detail in the next slide. First of all, I would like to explain what is March IC minus 10. It is a having complexity of 10n. Like we can see that write AV, read AV, write AV bar, read AV bar, write AV, read AV bar, write AV, read AV, write AV bar, read AV bar. So if we will collectively combine all these, then it will be having a complexity 10n and having March element 6, like from M0 to M5. The direction of this address, the direction of this arrow denotes that the address can be accessed in bidirectional. The address can be accessed from in the upward direction. The address can be accessed in the downward direction. The AV, here the AV or AV bar denotes that when we are going to write on the address, then we will write like 0 1 0 1. Like we will write 0, write 1, write 0, write 1, corresponding to the address maintaining Hamming distance is equal to 1. So proceeding towards the next slide. So this is the proposed reduced March IC minus test. So this is our work, that this is the algorithm which is made by us to detect the address decoder fault, that is the AFMA and all other faults we have discussed previously. So first of all, I'll discuss that what is the basic difference between March IC minus test and proposed reduced March IC minus test, which is our algorithm. So here the complexity directly reduces from 10n to 7n, because here what we did is that we have extracted elements M0, M1, M4, M5 from March IC minus and added an extra element RAV, which is M1 in the given March test below this one, this RAV, to form a new March test of complexity 7n. So through this algorithm, we will be able to detect the ADOF. So our target is to reduce the complexity, that is the length of the March algorithm. So finally, we are able to do this. Now I'll explain through example that how we can apply this particular March algorithm on any circuit, on any memory element. So suppose that I'm having memory of 2x2 array. So in 2x2 memory array, what will be the different addresses? So the different addresses will be like 0, 0, 0, 1, 1, 0 and 1, 1. So as I have already told that to detect any ADFs, our address should be such that it should maintain the criteria of Hamming distance is equal to 1. So our address, when we will going to apply the March element, so we will not apply like 00011011. We will apply something like 0001, then 11 and 10. So accordingly here you can see in the column that AD0, AD1, AD3 and AD2, that these addresses are mentioned corresponding to the March element. So here write AB means writing the alternate value. So here we will write 0, then write 1, then write 0 and write 1 in any direction. The arrow denotes like bidirectional, that is in any direction. So in the same way, read 0, read 1, read 0, read 1. So this is basically the way through which we are applying our March element. So this is March 0, like March element 0, this is March element 1, this is March element 2, this is March element 3, this is March element 4, and the value like RAB and write AB bar, this is called March phase. So this is March phase 0 and March phase 1. So these are the 5 elements which covers our reduced March IC minus test. Here we can apply write and read in any direction, and here we can apply it in upward direction, and this one in downward direction, and again the read AB bar will be in any direction. So this is the simulation setup. So this is the entire simulation setup which we have used to detect the faults. So this is the entire memory architecture which we have created using Virtuoso. So here we can see that this is the memory array, this is the 4x4 memory array, and this includes like row address decoder, column address decoder, the sense amplifier circuitry, write driver and preset circuitry will be included. So this is the entire thing which we have created for our simulation perspective. Now coming to the cell, like what each cell represents. So each cell represents 60 SRAM cell. So here in 60 SRAM cell, this is the architecture of the 60 SRAM cell, and you have Q and QB bar. These are the basically output and output bar of this particular 60 SRAM cell. This is the pre-charge circuitry which we have used, and this is the entire architecture of the sense amplifier which also contains the bistable latch. Now proceeding toward the next slide. So here fault injection and results, like how we are injecting the fault and how we are detecting the fault. So I have already told that there are basically 2 types of fault: intergate faults and intragate fault. So when we are talking about RDF1, then it will already shown previously that it will result into intergate faults, and for RDF3 it will result into intragate faults. So what happens that because of this RDF1, word like 3 is not getting accessed at all. That is, this is called AFNA faults. And now through this I'll explain that how we will be able to detect the AFNA fault. So this is the clock. This is the entire simulation setup which we have taken. So this is the clock. This is input A, B, C, D. This is word line 0, word line 1, word line 2, word line 3, Q0, Q1, Q2, Q3, and read operation. So our March element is something like write 0 and read 1, and then read 0, write 1. So what happens that suppose that maintaining that our Hamming distance should be 1, when we will like write 0 on word line 0, then it will be like write 0, on word line 1 it will be like write 1, and then again on word line 3 it will be write 0. But we can see it from here that output of the Q0 is something like, here we are able to write 0, write 1, but here at Q3 the cell is not accessed. So this is the problem which we have detected now, which we have injected. That cell is not accessed because of this RDF1. Now we want to detect this particular problem. So now again when we'll apply the read operation, that like read 0, read 1, read 0, read 1, that then during the third read operation we will be not able to detect the value read 0 because the previous read 1 will be stored. So here we can detect that our fault is detected. So if we continue the algorithm, then again this fault will be detected. So this is the entire way to show that how using this algorithm we are able to detect our faults. This is for intragate fault, that whenever RDF3 is included, then this is the algorithm which will show that how we will be able to detect the intragate fault. So assuming that March 0 and March 1 element is already applied, when we will apply March 2 and March 3 elements like read 0, write 1 and read 0 write 1 operation, like read 0, write 1 and read 1, write 0, like alternate value, then in this case we will be able to detect the double addressing fault. Like here we can see that during the second cycle, like what happens that word line 1 and word line 3 both will be accessed simultaneously. So here the problem of double addressing will be caused, which will be detected in the 13th cycle. So in this way we will be able to detect the double addressing fault. Now coming towards the next slide, which is conclusion. Improvise existing widely used March IC- algorithm to propose the reduced March IC- algorithm for in-field testing. Complexity of reduced March IC- is 7 as compared to March IC- which is 10 in complexity. The March pattern is applied to sensitize the defects, and it is able to detect the ADOs, and the efficacy of the proposed reduced March IC- is confirmed with a reduction in test time by 30%. These are the references which we have taken. Thank you. Any question?
Okay. Thank you, Anjali, for the nice presentation. Now
Thank
over
you,
to the
Swati.
question. Any questions
Yeah,
to
any
students?
So, 1 minute. Till now, we have not got any question from the audience.
Okay.
So, maybe session chair, maybe 1 or 2 questions.
Okay. So Anjali, has this new algorithm that you have developed, right? Has this been evaluated for all the possible faults in the memories? You have shown a case study of one of the faults, right? How it can be detected.
Yes, Swati. It's basically for address decoder faults. So, like what we did that the address decoder which we made. So, at every possible locations where we will get like address decoder faults, we have injected the resistance value, and so.
Okay.
So that for we verified, but for the PPT we included only like a few faults that we can show here. But at every possible location and with different resistance value, we are trying to check that it covers or not. So accordingly, that this algorithm is defined.
Understand. Okay. So, any specific reason that we have categorized it only for the field test and not for the regular manufacturing test, right? At time zero, for catching any of the time zero defects?
No, it's not like any specific reason. Basically, in the VLSI industry, what happens that MBEST is used for on-field testing. Like if we need if you go in terms of DFT, that ATPG is used for on-field testing. It's not possible to perform like ATPG in in-field. So like any BEST, like it's LBEST or MBEST, this can be used for on-field testing. So basically in life critical applications, MBEST is used. So this is the main advantage of any BEST. So that's why it's mentioned that if we are using any in-field testing, then this algorithm can be of beneficial.
But this can be used at time zero as well, right? That's
Yeah.
Okay. Yeah.
So, I have one question. So, what kind of fault you have considered? So, all kind of.
Yeah, all kind of address decoder faults, which is possible.
Only address decoder, not the memory cell. fault.
No, we targeted only the memory periphery. So in memory periphery, we targeted only the address decoder. So the faults which we included was address decoder faults.
Okay.
Yeah.
Okay, so if there is no question, then we can move towards the next.
Okay. Yeah. The next presentation is POSITGen, a verification suite for POSIT arithmetics. The presentation will be by Anara Kulkarni from CTAC. Over to you.
Hello, I am Shashikala Pattam Shetty from CDAC Bangalore. I will be presenting the paper POSITGen, a verification suite for POSIT arithmetic. Outline includes abstract, introduction, basis for POSITGen, POSITGen coverage model, random test vector generation, reference output generation for verification, POSITGen outputs, verification and code coverage analysis, conclusion and future work. Verification of floating point unit is a challenge due to its complexity to cover entire FP domain. This can be implemented by using random test vectors or simulation-based approach. These approaches has the issues like lack of coverage of corner cases and constraints based on operation. POSIT is a binary representation for real number and it has the similar challenge. Many software and hardware POSIT implementations have been verified by using random test vectors. In this paper, we present a verification suite for POSIT arithmetic. POSITGen provides both constant base and random test vectors to validate POSIT arithmetic unit. As a case study, we have used test vectors generated by POSITGen to validate in-house developed POSIT arithmetic unit on FPGA. POSIT is a binary representation for real number represented as a couplet POSIT n bits and ES. It has 4 fields: sign, regime, exponent and fraction. 3 basic types: 0, NAR, normal values. 1 rounding mode, RNE. POSITGen provides native POSIT in and POSIT out verification paradigm for POSIT arithmetic units. Next we'll see basis for POSITGen. There are major factors considered in POSITGen. First is dynamically varying fields of POSIT, where the size of sign field is fixed and the size of other 3 fields changes. Second is constraint model, which are based on operation type, input and data patterns, etc. N-bit POSIT generates 2 raised to n-bit patterns, which are represented as NPAT. Based on varying fields of POSIT, POSIT domain is divided into 3 subsets. POSIT domain subset 1 includes sign and regime bits only. It gives 0, NAR and normal values. Normal values include both positive and negative minimum, maximum and previous to maximum POSIT values. It gives total 8 NPAT. POSIT domain subset 2 includes sign, regime and exponent bits only. It covers normal POSIT values. Number of bit patterns is based on the range of ES bits. NPAT can be calculated by using equation where NPAT is the sum of 2 raised to sign into R into 2 raised to X as X goes from 1 to ES. POSIT domain subset 3 includes sign, regime, exponent and fraction fields where NPAT is calculated by using the equation where NPAT is the sum of 2 raised to sign into R into 2 raised to X, where X is calculated based on the size of regime bits, where regime bit size goes from 2 to n bits minus 2. For example, for POSIT 16.1, regime size is 4, fraction bits will be 10. So, number of patterns can be calculated by using the equation where NPAT is 2 raised to sign into R into 2 raised to ES into 2 raised to fraction. So it gives total 8192 bit patterns for POSIT 16.1 where the size of regime is 4. Next we have considered POSIT pattern distribution statistics. In case 1, bit patterns and size of regime is considered, which specify number of bit patterns represented by the given size of regime. In case 2, range of POSIT for given regime size can be determined by calculating the maxima and the minima for that regime. So this helps to cover entire POSIT domain with corner cases. Next is the POSITGen coverage models. In this we will see operation independent model. The first one is the basic types, in which operands can be of basic types. So for given POSIT format, let P be the set of POSIT basic types. So the Cartesian product of these sets enumerates all combinations of operands for given binary operation. So this model is applicable for all 3 subsets of POSIT domain. The next one is the near base values. In this, POSIT basic type is treated as a base value and this base value is considered as a boundary value. So this model generates operand such that output of the operation will be nearer to these boundary values. This model is also applicable to all subsets of POSIT domain. The next one is the directed RNE. POSIT supports one rounding scheme, that is RNE. So this model generates test vectors such that the output of the operation will make it to invoke the rounding scheme. This model is also applicable to all subset of POSIT domain. Next model is the near to positive negative max pos. There is no overflow in POSIT. Here we consider output and intermediate results which are near to the max pos. So this model covers the corner cases towards the maximum possible value in POSIT. So this model selects the operands such that one operand can be of max pos minus 1, max pos minus 2, and the second operand can be of any POSIT number having regime bits n minus 1, n minus 2, and so on. So this model is applicable for all three subsets of POSIT domain. Next model is the near to positive negative min pos. There is no underflow in POSIT. This model generates output operands such that the output of operation will result into min pos or near to min pos. So subtraction of negative max pos and negative non pos will result into negative max pos, as the max pos is the smallest possible number represented in POSIT. Here we also consider min pos value with non pos for addition and subtraction. This model is also applicable for all three subsets of POSIT domain. In this, we will see operation dependent models of POSIT-gen. The first one is the operands cancellation. This model selects operands which are very close in magnitude. So it selects operand 1 and operand 2 such that regimes R1 and R2 and X1 and ES2 are in such a way we need to select R1 and R2 where R1 should be less than or greater than R2, ES1 and ES2 are not equal, and we can select fraction bits F1 and F2 by setting the offset. This model is applicable for addition and subtraction only. So as shown in the graph, first we need to select operand 1 such that it will have the regime bits from 2 to n minus 1, and then by calculating the size of R1 we can calculate the size of R2 having the certain difference. Next is the random test vector generation. This model generates operands randomly. It considers regime bits having size 2 to n minus 1. ES and fraction bits are selected randomly by calculating the range and by selecting the value from that range. No constraints applied to this model. This model generates test vectors for POSIT 16.1 and 32.2. Next is the reference output generation for verification. To generate reference output, we have used SoftPOSIT library, which is written in C, and POSIT-gen framework uses C language. Next is the POSIT-gen output. Table shows the number of test vectors generated by POSIT-gen models for POSIT 16.1 and POSIT 32.2 for addition and subtraction. Verification and code coverage analysis. As a case study, we have used POSIT-gen based test vectors to validate in-house developed POSIT arithmetic unit on FPGA. This part will be covered by co-author Anish.
For verification and code coverage analysis, we have developed 3 POSIT functional units using Verilog RTL. The functional units are POSIT addition subtraction, POSIT fused division and square root, POSIT fused multiply or accumulate unit. These 3 functional units are verified, validated and performed code coverage analysis using POSIT-gen test vectors, random test vectors, IBM FPGen test vectors converted to POSIT, and Berkeley TestFlow test vectors converted to POSIT. Code coverage analysis and comparison. Table on the left side depicts the code coverage analysis of fused to multiply accumulate unit with the random and POSIT-gen test vectors for n equal to 16 and 32. The matrices which are used for code coverage analysis were branch, statement, FEC condition and FEC expression. From the table, it is clearly depicting that POSIT-gen based test vectors for FEC condition and FEC expression are giving better coverage as compared with the random. Table on the right side depicts the code coverage analysis of FPGen and IBM Berkeley test flow test vectors converted to POSIT. From the table, it is clearly depicting that the four code coverage matrices are almost closer in value. This slide details the code coverage analysis of POSIT fused addition and square root and POSIT addition and subtraction module. Table on the left side depicts the code coverage analysis of POSIT fused addition and square root module using random, POSITGen and FPGen translator test vectors. From the table, it is clear that the FEC expression code coverage metrics for POSITGen are giving better code coverage as compared with the random and FPGen translator test vectors. Table on the right side depicts the code coverage analysis for the POSIT addition and subtraction module by using random and POSITGen and FPGen translator test vectors. From the table, it is clear that POSITGen test vectors for FEC condition and FEC expression gives better coverage in value. Conclusion. POSITGen provides native POSIT in and POSIT out verification paradigm for POSIT arithmetic circuits. POSITGen test vectors are based on constraint and corner cases. Proposes three classes of test vectors: POSITGen test vectors, random test vectors, IBM FPGen and Berkeley test float test cases converted to POSIT. POSIT fused multiply accumulate and POSIT division square root and POSIT addition subtraction modules are verified and validated in simulation using the above mentioned test cases and performed code coverage analysis with these test vectors. POSITGen based test vectors provides better coverage in FEC condition and FEC expression and comparison with the random test cases. On the future work, we have to generate more test cases for 64,3 and verify and validate the POSIT hardware arithmetic circuits. On the POSITGen verification framework, we have to extend the operation for class conversion, comparison, and maximum operations. Also, we have to validate the POSIT hardware arithmetic unit using POSITGen and random test cases on FPGA. Also, we have to perform formal based verification and validation of hardware arithmetic units. Thank you.
Hello.
Thank you, Shashikala and Anish, for the good presentation. Any questions from audience?
Check. So, till now, I have not got any questions from audience.
Okay.
So let's ask one question, a very basic question. So how does a POSIT kind of dependency is actually getting used in actually real life processor or computing environment? So I'm new to the POSITGen, but still I want to know what is the basic comparison between this.
Yeah, hello. I'm audible.
Floating point and POSIT number.
Sir, currently in the research community, this POSIT number system is getting adopted recently only. So further change towards making us a coprocessor and building a computing system is also under research here only. There is no chip came out for computing, but an FPGA based accelerator for AI, ML or such kind of arithmetic applications, it came out from the different universities. Like in India, IIT Madras, IIT Mumbai, and CDAC and IAC providing means they're providing solution for on FPGA with this arithmetic circuit for either hardware accelerations or as a coprocessor. But as in the real chip or a physically realizable chip wise, there is nothing. It is still under development in the research community. So we are also facing one difficulty to compare the actual values. Whatever we are also. Tomorrow we are presenting one more paper for the hardware realization. So we are unable to compare the equivalent ones because from research community, the actual chips which are not coming out. And still this number format and associated arithmetic circuit verification and validation frameworks are still in a research phase.
Okay. Thank you.
Okay. Yeah, one question from my side. In the future work, you have mentioned that extending this POSIT-Gen to cover all operations, right? So I'm just curious to know what percentage of operations are covered today with the existing POSIT-Gen.
For this work, we have done fuse to multiply, accumulate, then division square root are considered for this particular work. But from our organizational perspective, we have done currently all the 64 operations of the RISC-V ISA compliant POSIT.
Okay. And we have good results on
for this work. We are yes, ma'am. Yes, we have a project for this. Yes.
Okay. And you mentioned it is validated on your in-house FPU, right? Built into the FPGA. So is it generic enough for all the FPUs, or is it something specific to your FPU architecture that you have validated?
No, ma'am. How we have validated is we have an in-house developed FPU, which is FPU modules like FPU arithmetic circuits. We have made a Pi engine, which uses FMA and division square root.
Okay.
Basically, multiply, accumulate, and division square root. So we made an architecture with the POSIT plus IEEE 754 also. Then we have compared the results in terms of the byte-wise accuracy.
Okay. Any other questions from anyone else? Okay. Thank you to the presenters and reports. We'll move on to the next presentation. Training neural network for machine intelligence in automatic test pattern generator. The presenter will be Soham Roy from Auburn University. Over to you, Soham Roy.
Everyone, and welcome to my talk titled Training Neural Network for Machine Intelligence in Automatic Test Pattern Generator. My name is Soham Roy, and I am a PhD candidate of Electrical and Computer Engineering Department at Auburn University in Auburn, Alabama, USA, under the supervision of Professor Spencer Millikan and Professor Vishwani Agarwal. Today, I am going to give you some prior work and motivation for this study. Then, I will explain how machine intelligence is applied to our study. I'll also discuss about the possible directions leading to a formal training procedure of the artificial neural network. I'll then discuss on how we resolve conflicted training data patterns using some trivial mathematical calculations, followed by the proposed recursive training algorithm which makes our ANN an evolving ANN. I will also analyze our experimental results thoroughly. Finally, I will conclude this talk by briefly point out the major contributions of this study and future avenues that may be taken to achieve more interesting results. The Dee algorithm in 1967 established ATPG as a standard method of generating high-quality tests for the logic circuit industry. However, since its introduction, it was noticed that ATPG can have frustratingly long runtimes for some circuits. Numerous later studies lowered ATPG runtime in numerous ways, but since the introduction of BODEM in 1981, the theoretical upper limit of ATPG runtime has remained constant. Let us see an example. For a circuit with I inputs, these I may include scan latches in case of scan-induced circuits. ATPG may need to simulate 2 raised to the power number of primary inputs of the circuit vectors to find a test. Although ATPG algorithms typically find tests without simulating close to this many vectors, this upper bound still exists and is occasionally seen in modern circuits. To avoid this upper limit, most ATPG algorithms employ backtracing subroutines. These subroutines trace backwards through a circuit starting from an objective, such as exciting or propagating a fault, and attempt to find input assignments which accomplish the objective. Multiple backtraces from an objective may be required to meet the objective. But if these input assignments accomplish the final goal, that is find a test for the fault, then at most I input vectors must be simulated, which is nothing compared to the theoretical maximum of 2 to the power I. However, this ideal situation presumes no backtracks occur during ATPG. When the backtracing subroutines reach a circuit input and assign it a value, this assignment may block the current or future objectives. When this occurs, ATPG must undo or backtrack to some previous assignment, which means ATPG wastes time simulating unnecessary input vectors. Beyond PODEM, numerous ATPG algorithms attempt to reduce runtime by creating fewer objectives, but to our knowledge, no studies compare ways of backtracing from an objective. When backtracing, it must decide which direction to go, but choosing a wrong direction may result in a backtrack. To develop a new backtracing strategy, I look towards the technology of machine intelligence. Machine intelligence describes a broad category of algorithms that automatically program themselves through experience. This experience can come from unclassified data which the program finds patterns in, which is unsupervised learning, or the experience can come from a database of training problems with desired outcomes, which is supervised learning, or the experience can come from iterative re-evaluation and adjustment, which is reinforced learning. Recently, International Test Conference ITC 2020 published our research work, which shows that an artificial neural network ANN can combine multiple heuristics to guide an automatic test pattern generator ATPG with fewer backtracks than required by guidance from any single heuristic. We are going to reuse same ANN structure that has a single output neuron and a single layer of hidden neurons, which is sufficient to accommodate the training data volume. Conventional PODEM ATPG applied to hard-to-detect and easily detectable faults in selected benchmark circuits provide training data for nodes marked as success if the backtrace leads to a test, or failure if it results in backtrack. Each entry in the training data pattern comprises of the COP controllability, the circuit depth, and the driving gate type given as a one-hot string on the decision point. Let us try to figure out the motivation of this study. These are the results we obtained from our own work of ITC 2020. Since results depend heavily on benchmark sizes, we chose to normalize plots with respect to ANN-guided backtracing results, which we believe more accurately reflect the goal of ATPG research, that is to reduce ATPG runtime by a factor as opposed to by a constant. Therefore, positive plots in these figures reflect results favorable to the machine intelligence. The results on decreasing backtracks show promising results. We see that for most benchmarks, using the ANN in lieu of conventional heuristics decreases the number of backtracks, often considerably so. As we can also see that the improvement in ATPG performance for some benchmark circuits, including some larger benchmarks such as C3540, C7552, C2670, and C432 did not perform well. To motivate this work, we repeated the work of ITC with minor changes. Firstly, training patterns were generated using PODEM applied to 100 hard-to-detect faults in the 3 highest depth circuits, that is C6288, C3540, and B05. Secondly, the trained ANN was then used to guide a PODEM applied to the 100 hardest to detect faults in each of the 24 benchmark circuits used in the original ANN, that is ITC studies ANN. This figure compares the total backtracks with those of conventional PODEM using distance and COP heuristics. One difference in our evaluation procedure, as stated in the ITC study, is that we did not include backtracks from aborted faults. We refer ITC studies ANN as the original ANN to distinguish it from the ANN developed in this study identified as the new ANN. The ANN training in the ITC research study was ad hoc and rudimentary. Therefore, this study provides a formal training that may elevate ANN-guided PODEMs at performance. This study examines such a training method. The training recursively uses ATPG data generated from hardest to detect as well as easily testable faults, resolves conflicts in data patterns, example when different ANN outputs come from similar inputs, and discards data that does not improve the guidance of ANN. We believe remedying the outliers just mentioned a few slides before requires addressing several aspects of the ANN training procedure. Our investigation led us into following observations. Firstly, the ANN was trained with ATPG data from high-depth circuits. Since C3540 causes worry, I retrained the ANN with just C3540, but still the ATPG performance of this circuit did not improve. Therefore, I retained the 3 high-depth circuits for training. Secondly, the training data patterns may lead to increase in training error of the ANN and thus degrade its guiding ability. This is explained in details in upcoming slides. Thirdly, all faults do not provide useful training information, and pre-selection of faults for training may unnecessarily increase the training data volume without benefit. Upcoming slides gives a novel method of training the ANN considering three aspects. That is, the training error of ANN must be kept low by adjusting the number of hidden neurons. Training data from a fault must be accepted only if guidance from the resulting ANN reduces backtracks, and the faults used for training data generation should not restrict it to be hard to detect faults. In fact, a fault provides useful training data as long as it reduces backtracks. And finally, the ANN may enter a zone called catastrophic forgetting when it forgets information contained in a large training data volume. Such consideration in training improvement is worth exploring in the future. To remedy conflicting training data patterns, we collect patterns with identical features into groups and then replace each group by a single representative pattern with common features. Since these patterns are derived from actual ATPG runs, the label of a pattern is either 1 indicating success if it belongs in a backtrace leading to a test, or 0 indicating failure if it results in a backtrack. We count the number of 1 and 0 labels in the group, and the representative patterns label is given in the next slide based on a formula. In this slide, a conflict is illustrated by the sample training patterns in figure, where the first 3 patterns have a conflict. This is resolved in this figure, where the 3 patterns are replaced by a single representative pattern with a label count equals 1 divided by number of label 1s plus number of label 0. That is 2 divided by 2 plus 1 equals 0.67. The algorithm is to develop an evolving ANN guided ATPG is illustrated in the figure. We select large depth circuits C6288, B05 and C3540 from ISCAS 85 and ITC 99 benchmarks. The ANN structure is same as in the ITC recent study, and parameters such as number of hidden neurons and mean square error are initialized. COP-based PODEM is applied to a set of 100 hard-to-detect faults, and number of backtracks is recorded to be minimized through recursive learning. The training starts by using 50 hard-to-detect faults to generate a training database, followed by ANN training to check mean square error and record the corresponding number of hidden neurons simultaneously. This process continues until mean square error starts saturating and corresponding mean square error and the number of hidden neurons is recorded and the ANN is retrained. The similar process is continued for 100 easy-to-detect faults. To evaluate the training, the ANN-guided ATPG is applied to 100 hard-to-detect faults of the same training circuit. If backtrack count decreases, then 100 more hard and easy-to-detect faults are added to the training of the ANN as the number of hidden neurons and mean square error are restored. Discarding the corresponding training patterns from the training database, and another circuit is selected to reiterate the same process until one of the following conditions is satisfied. We kept these conditions to satisfy our need, but one can always change these conditions. These conditions are the number of backtracks should be reduced to at least 50. At most 100 hard and easy to detect faults should be used for training. And finally, the ANN contains at most 100 hidden neurons. The graph shows how the new ANN performs on 100 hard to detect faults across benchmarks as compared to the original ANN. In terms of backtracks, with few exceptions, the new ANN does the same or better in reducing backtracks compared to the original ANN, especially for larger circuits. This experiment used all faults, that is testable and redundant faults, to show the efficacy of guidance by the new ANN using the proposed training procedure. Clearly, the new ANN performs better with fewer backtracks than the original ANN as shown in graph, reaffirming the value of the proposed training technique of this study. The graph has some notable observations. First, C17, B02, and B01 have no reconvergent fan-outs and therefore have no backtracks. Of course, there is no scope for reducing backtracks by new ANN guidance. Second, except C1908, C432, C499, B12, and B05, the new ANN exceeds expectations in terms of back performance based on reductions in backtracks. Third, the new ANN is able to reduce backtracks for B09, but the CPU time increases. Possibly, more time per backtrace is used in order to reduce backtracks by expensive evaluation of weights and biases of ANN edges that involves matrix multiplication and computation of sigmoid function. Fourth, the new ANN heuristic does not perform as well on a few circuits compared to the original ANN, but it still outperformed the conventional heuristics like distance and COP, except in case of C432. Here in this graph, it illustrates that CPU time remains constant for smaller circuits and reduction for high-depth circuits is observed, perhaps due to simultaneous reduction in backtracks and backtraces. The contributions of the study are listed. Firstly, a technique to resolve conflicts among ANN training data. Main benefit of conflict resolution is improved ANN accuracy as evident from reduction in the mean square error during training. Secondly, a training technique for selecting faults using a recursive training method that dynamically trains an evolving ANN as opposed to the training with a pre-selected set of faults. ATPG data from a fault is retained only if the trained ANN guidance discontinues to further reduce backtracks over those from conventional heuristics, that is distance and COP. Both hard to detect and easy to tested faults are sampled as opposed to only hard to detect faults in our ITC recent studies results. This prevents the training data from being overwhelmingly failure oriented. And thirdly, an improved assessment of the quality of the ANN guidance by modifying the backtrack count procedure. I count backtracks only for the faults that are detected or found redundant. Earlier work of our ITC resistance study also included backtracks from aborted faults, which distorts the count. This study provides several avenues to be explored. First, our focus was on reducing backtracks, but the performance of backtraces, particularly in reconvergent fan-out-free circuits, can also be improved. Secondly, our exploration for eliminating backtracks has a cost in CPU time. Thus, the sweet spot may be found where the reduction of backtracks would be optimum for minimizing CPU time. Third, finding untestable redundant faults earlier can make ATPG for the entire circuit faster. Fourth, recent work has demonstrated that arbitrary random circuits can generate limitless training data. Fifth, this study is demonstrated on academic benchmark circuits and not on larger industry standard circuits. The authors believe that the ANN-guided ATPG performance trends are quite promising and likely to scale on a wider variety and large set of designs to show broader capabilities in future. Finally, there may be other features such as scope and those related to fan-out or reconverging signals that can add to the capability of the ANN. Yet another area is to examine ANN structures beyond the single hidden layer. I would like to end by thanking each and every one for their time and attention. Hope in the future I can give you encouraging results based on this study. The floor is now open for question and answer.
Thank you, Soham Rai, for the good presentation. Any questions from audience?
Thank you, Swati.
Let me see just 1 minute. So, are there any questions from audience? No. So, from external audience, we don't have any questions. So I have one basic question. So, what kind of ANN architecture you have used?
So I have used a normal basic feed-forward single hidden layer neural network. That's the basic neural network I have used. Yeah.
Yeah. And what kind of activation functions and all the things you have used?
So I have used sigmoid as an activation function, and I have used Adam optimizer for my optimization function. And what else? I think, yeah. So, yeah.
And among all the machine learning techniques, as neural networks, ANN, CNN, DNN, these are the most actually compute intensive machine learning model. So why do you use so complicated one? So instead of we can go with very simplistic any other machine learning model to do the same thing.
What I believe that this feed forward model is the basic model. So in spite of using those convolutional or DNN model, what we thought that let us first try with the very basic model first. And in the literature survey, we have found that this basic model can solve almost all the problems. So that's why we use this one. And as we can see in our results also, we found a substantial improvement in the ATPG performance.
Okay, thank you.
Okay. Yeah. One question from my side. So for some circuits like C1908, right, you have mentioned the number of backtraces are higher with the new ANN compared to the original. So and you have also mentioned some possible reasons why it could be higher, right? So what are the plans to address them? Just curious to improve the new ANN to address those as well.
Yeah. So the possible plan what we use. So already we have studied those outliers. So the possible plan is to increase the more number of features and incorporating more complex ANN. So rather than using single layer, we may extend up to another layer and we can see more improvement in the results.
And another plan what we thought but we haven't executed yet, that is, so right now we are only executing our training data extraction feature, training data extraction strategy on only particular node in a circuit. What we thought that probably we can go 2 level back and 2 level forward, and then we can get more information. So if we can get more information, we perhaps think that probably the improvement we can see more substantial.
Okay. Any questions
from any other people? So other, you can say, participant or presenter can ask questions if they have. If you don't have question, then let's thanks Soham, right?
Thank you.
Okay.
Let's
Thank
proceed to the next.
Yeah, we'll move on to the next presentation. So the next one is neural network based indirect estimation of functional parameters of amplifier by extracting features from wavelet transform. Presentation will be by Supriyo Srimani from IIEST Shibpur. Over to you, Supriyo.
Hello everyone, myself Supriyo Srimani, a research scholar of Indian Institute of Engineering, Science and Technology, Shibpur. Today I am going to talk about my work on neural network-based indirect estimation of functional parameters of amplifier by extracting features from wavelet transform, co-authored by Dr. Kasturi Ghosh and Professor Hafizur Rahman. This will be the outline of my talk. First, I will discuss about the properties of analog circuit and its challenges during testing. Next, I will discuss on the test stimuli used in this work. The proposed technique will be discussed in two parts. First, discrete wavelet transformation and multi-resolution analysis, then artificial neural network as the prediction algorithm. Then the proposed methodology is discussed along with the result on an operational amplifier. Finally, I will conclude after discussing the advantages and disadvantages of this methodology. We are all aware that analog circuit deals with continuous signals, which leads to nonlinearities. In addition, the input-output relationship of analog circuits are very complicated in nature. Large varieties of analog circuits exist in today's technology, like filters, amplifiers, transmitters, receivers, ADCs, and many more, which operate in a wide range of frequencies. So it is very difficult for a test engineer to develop a testing technique for these varieties of circuit. Technology scaling over the first few decades has ensured that the manufacturing cost per transistor has decreased steadily. However, the test cost per transistor has not decreased with process advancement. As the number of transistors in an integrated chip continues to increase relentlessly, test cost has emerged as a major showstopper for further advancement. According to the ITRS dataset, test cost is now a major part of the manufacturing cost. Therefore, there is a pressing need to reduce the test cost in high volume of chip manufacturing. Also, it is noted that analog test cost per transistor is almost 10 times of that digital test cost per transistor. The main objective of this work are to develop a test procedure for faster production techniques of analog and mixed signal circuits has been demonstrated in this work. This will lead in reduction of the hardware test cost, testing time than conventional performance measurement technique. The new test algorithm predicts the functional parameters of the circuit under test from the output test response using wavelet transform as a preprocessor and artificial neural network as a prediction algorithm. The proposed algorithm is also validated with a practical IC TLV2762CD from Texas Instruments. Test stimulus is an important parameter for higher test coverage. Designing an optimal pattern of testing should meet the necessary specification, like detection of preferably every false in the pre-assumed fault model. Number 2 is that simplicity of generation or storage means low overhead. 3 is the shorter testing time. Keeping this in mind, a pseudo-random based test stimuli has been used to excite the circuit under test. The DAC converts LFSR generated pseudo-random bit sequence into analog signal. For random input signal in T shown in the figure, the output of a linear analog circuit is a new random signal YT which can be considered as a linear transformation of the input random stimuli of the analog CUT. In this work, the random input stimuli is generated from a 12-stage internally XORed LFSR followed by DAC. The power of the signal is fixed based on the allowable range of the PDK and the CUT. There are some advantages of pseudo-random signal, like a pseudo-random signal generated from a LFSR has a property of being spread spectrum, which is that the spectrum power of the pseudo-random signal is spread over the wide range of frequencies. Another advantage is that a pseudo-random signal will excite the CUT with large number of frequencies simultaneously with varying amplitude levels and will thus allow testing to be performed through the outputs of the CUT. In this slide, I will try to give a brief introduction on discrete wavelet transformation used for feature extraction for the proposed work. Fourier analysis is a frequency domain analysis of a signal, so the information about the spatial distribution is missing in case of Fourier analysis. On the other side, wavelet decomposition characterizes a signal in both time and frequency domain, which appears to be very advantageous for testing of analog circuits. A discrete wavelet transform of a sample signal is denoted by this equation, where phi is the mother wavelet. A mother wavelet is an oscillating function with finite energy and zero average. In this work, Debuchy's wavelet has been chosen as a mother wavelet as its order can be controlled as per the required problem. A signal can be decomposed with the help of wavelet transform into different low frequency and high frequency levels by the means of low pass filter and high pass filter to produce a family of higher and organized components of signals called approximation and details respectively. The figure in this slide shows three-level decomposition of a signal. At each level, half band low pass filter remove half of the frequencies. At each level of the wavelet coefficient is reduced by a factor of 2, which is demonstrated by a down arrow and 2:1. For a three-level decomposition, C3 is the approximation level with the lowest frequency band and D1 to D3 are the detail or higher frequency band. A generalized notion for the signal by the following set of coefficients arranged by this shunt. The dimensionality of the dataset at the classifier input is chosen to keep as small as possible to obtain a higher accuracy with lower computational time and load. Therefore, feature extraction and feature reduction is necessary. First, features are extracted from the preprocessed raw dataset, then the features with low variance are rejected. 16 different feature extraction algorithms was used in this work, like mean absolute value, energy, Shannon's entropy, log energy entropy, RMS, mean, standard deviation, skewness, kurtosis, form factor, trace factor, shape factor, impulse factor, margin factor, mobility, and complexity. Features extractors, the previous feature extractors were separately used for detail coefficient of each level and approximation coefficient of the final level, which is level 10 for this work, found by wavelet decomposition. So a total number of 16 into 11, so that is 176 numbers of features are acquired. Mean max normalization is then used to represent a dataset between 0 and 1. To reduce the size of the input dataset, principal component analysis has been used. In this slide, I will try to give a brief overview of artificial neural network, which has been widespread application for the prediction and similar problems. The figure shows a schematic of the mathematical model of an artificial neuron, which consists of an input signal Xj, the input synapses for the input synapse J, connected to a neuron K, which is then multiplied by the weight Wkj. The weight Wkj, if positive, if the associate synapse is excitatory, and if negative, if the synapse is inhibitory. An error for summing the input signal weighted by the respective synapse of the neuron. An activation function for limiting the amplitude of the neuron. The activation function limits the permissible amplitude range of the output signal to some finite value and also a bias term. The process of training a neural network requires detection of the function and tuning the weights of the network for optimizing the performance. The performance goal is maximum acceptable difference between the actual output and the predicted outcome. If the difference between the original value and the predicted value is less than a desired target value, then the training is complete. Otherwise, the network is again trained by tuning the weights with the difference of actual value and the predicted value. In this work, a network training function train LM is used, which update the weight and bias for the network in accordance to Levenberg-Marquardt optimization process. The functional parameters selected for creating the network to the test amplifier is listed in the table. In this slide, I will give the overview of the methodology used in this work. In the first phase, 1000 CUT instances are generated by Monte Carlo simulation, varying the device parameters like VTH, TOX, mu n, etc. Then the performance parameters have been obtained for those CUTs using SPICE simulation. Next, the output response is captured for the same CUTs excited with the pseudorandom stimuli. Wavelet multi-resolution analysis is then applied to the output signals, and 16 distinct feature extension processes is then applied to the detail coefficient and the approximate coefficient. The neural network model is then created with proper weight and bias. In the testing phase, the same test stimulus is applied to the testing CUTs. The response of the CUT is captured and feature extraction was performed using the wavelet coefficient. The functional features means the signatures is then evaluated using the neural network model created earlier during the first phase to compute the device specification. The circuit topology of CMOS operational amplifier is shown in this figure, and the topology used in this work to produce the transient response of the pseudorandom signal is given in this figure. The process parameter considered for generation of the circuit instances by Monte Carlo simulation are listed in this table. These process parameters have been taken for both PMOS and NMOS of the op-amp. As you can see that some mismatch parameters, mismatch transistor parameter is also taken. The functional parameter selected for validation of this algorithm is given in this table along with their nominal values. In this slide, the decomposition coefficient relating to the output response is shown. The random output data is sampled within 0 to 4.09 microsecond with 2 nanosecond interval. Since the output signal is sampled at 500 MHz, the component with the highest frequency value that dwells in this signal is 250 MHz. At the first level, the signal containing with 4096 samples is passed to the high pass filter and the low pass filter. The outputs are subsampled by 2. The output of the high pass filter denoted at the first level of BWT coefficient shown in the first figure. The 2048 sample depict the signal in the range of 125 to 250 MHz. The low pass filter output, which also consists of 2048 samples but spread within 0 to 125 MHz frequency band, are further decomposed by passing them into low pass and high pass filter, generating a subsample signal with 1024 samples. This procedure can be continued till 1 DWT coefficient can be calculated. In this plot, the x-axis denotes the value of the functional parameter generated by the direct simulation, and the y-axis represents the predicted value using the proposed technique of the corresponding functional parameters. The ideal correlation amongst the predicted and simulated specification are highlighted by a perfect 45-degree plot. For 200 test CUT, the RMS and the peak errors between the directly simulated and predicted specification shows the accuracy of the proposed indirect testing algorithm. The proposed technique is also validated for a commercially available IC TLV2762CD by Texas Instruments for the same performance parameter using the same test stimuli and the circuit configuration. 45-degree plot among the simulated and the predicted plots shows the accuracy of the algorithm for practical IC specification. To conclude, I'll summarize the advantages of the proposed methodology. So using this proposed methodology, the overhead of the test cost of functional testing can be reduced significantly. Also, it will help to reduce the test time, helping for mass production. Prime advantage of this methodology is that it requires measurement of the output voltage only for a given pseudorandom voltage. Therefore, this method is relevant to the circuits where the internal nodes are not available. Due to use of the pseudorandom signal, the design of the complex circuitry and the cost to construct the test signal also reduces. The proposed methodology test algorithm can be implemented into a test board that can be treated as an inexpensive tester for mass testing. Thank you.
Yeah. Thank you, Supriyo, for the presentation.
From
Any
audience side,
questions
we don't
from
have any.
audience?
From audience side, we don't have any questions.
Okay.
So we have one question for previous presenter, but already the presenter is already. So you have extracted 16 parameters using this wavelet transform. All the 16 parameters or 1 or 2 parameters?
No, sir. Actually, for 10 level of wavelet coefficient, for each level we have extracted 16 features. So a total number of 16 cross 11, 176 features we have extracted for each output response.
Yeah, Supriyo, one question from my side.
Very compute intensive.
Hello? Yes, madam. Yes. Yes, sir.
Now it can be very compute intensive. Because you need to extract a lot of parameters using wavelet transform.
Yes, sir. It is initially it is very computational complex, but as it is a batch process or it is for use for the mass production. But initially, if we extract the features, these features can be used for many for batch iteration.
Okay. I don't have any questions. So. Hello, Swati. Hello. So, any other presenter have any questions? Supriyo? Hello, Swati. So if we don't have any question, then you can close the sessions. Thank you, Swati, for chairing the sessions. So we're giving you a virtual token for appreciation for the chairing the sessions, and we'll set the momentum for up to you to your email address. So thank you all the presenter. Thank you all the audience of the technical sessions. Thank you all the team member of the technical sessions. Now the technical sessions 2C is formally concluded. Let me ask one more time, Swati. So can we close the session, technical session, Swati?
Hello, can you hear me?
Yeah.
Okay.
So we're able to hear you. So thank you for
some network problem at my end.
So thank you for chairing.
Yeah, thank you, sir.
Give you
Thank you.
Virtual token of appreciation for chairing the sessions, and we'll save the moment to your email address.
Sure, thank you.
And
thanks everyone
all
for
the
joining.
Presenter, all the audience, all the team member of the technical sessions. Okay, so now we can formally conclude the sessions. I think it's done.
Okay.
Thank you.
Okay.
Thank you, sir. Thank you.
Thank you.